So if you're ever reading about quantum mechanics or quantum chemistry, as I suppose one does, you will undoubtedly encounter the quantum harmonic oscillator system, which is useful for modeling vibrational motion in molecules. And often what I find is if I prepare a spreadsheet in Excel, that helps me gain a deeper understanding of what is going on, because it makes me go through all the formulas, make some plots, and interpret what goes in and what comes out of that model accurately. So that's what we're going to do in this video. So I'm going to show you a textbook with as references for the quantum harmonic oscillator. I'm going to show you the equations that go into it. We're going to model those in Excel, and then we're going to discuss the output. So let's get started. Okay, so I'm following along the Atkins and DePaula physical chemistry textbook. I believe it's the 8th edition. And this is the section on vibrational motions. That's where they bring in the quantum harmonic oscillator. And I'm not going to go through the full derivation of everything that's in here in terms of all the equations and where they come from, although I will review the ones that we'll be using in the model. But crucially, what I'm interested in showing are the wave functions. For example, this is for the ground state, v equals 0. And rebuild this image in Excel. It won't be this three-dimensional stacked, rather beautiful image of plots, but we'll get them all out as individual line plots. So let's flip over to Obsidian, where I have all the equations we're going to use, and look at that. Okay, so let's take a look at the equations that we'll use in the spreadsheet as we build our model. And virtually all of them came from Atkins and DePaula Physical Chemistry 8th edition, Chapter 9. There was a reduced mass equation I got from the quantum harmonic oscillator section of hyperphysics, and that link is right there. So just to review, the force in a classical harmonic oscillator is negative kx, where k is the spring constant. When you're looking at a molecule, that's a bond property of the bond between two atoms. The potential energy V is equal to 1/2 kx squared. So it takes on the shape of a parabola in which the oscillator can be. And when you take it to the quantum treatment, you need to use it with the Schrödinger equation. So you can see how we have h psi plus v psi equals e psi. And that comes out to be, there's the h operator, h hat, acting upon psi. And then 1/2 kx squared psi equals e psi. So that's how you insert this potential energy down here into this Schrödinger equation. And then as you solve it, you get the energy levels. So first you define omega as the square root of k over the reduced mass. And the reduced mass is the product of the two masses divided by the sum of the two masses, since we're only looking at a diatomic molecule here. The EV, which is the energy at that quantum number v, I'll just keep saying v, so at the v level, which can be 0, 1, 2, and on up in the integers, is v plus 1/2 the quantity h bar omega. And then wave functions, we have alpha as defined here, gamma as x over alpha, which defining it as gamma really makes it easy to plug it into this complicated function here, which is the solution to the Schrödinger equation, which would be psi v, so psi of the energy level v, is a normalization factor, which we'll get to, a Hermite polynomial, and an exponential function. So what are the Hermite polynomials? They're well known in mathematics. As they affect us here is that they're the solutions which actually allow us to use the Schrödinger equation to model the system. So as you go up through each v level, 0, 1, 2, or 6, you change your Hermite polynomial that's used to model it. So h0 is a very simple function. It's just 1. So up here, it changes nothing. It's because you're multiplying by 1. And then at 1 is it's 2y. At 2, it's 4, not 2y, 2 gamma, sorry. At 2, it's 4 gamma squared minus 2. But when you get to level 6, it becomes this complicated expression here. And that's why I cut out levels 3, 4, and 5, is because those would tend to be humongous formulas to enter into Excel. And I feel that just plotting out these 4 levels show what's going on as V increases. And so then we have finally the normalization factor, which of course makes the wave function quadratically integrable, which means that its probability density sums to 1. So with that in mind, let's head over to Excel. Okay, so let's look at the spreadsheet we're going to build before we actually dive in and build it. So the ultimate goal of the spreadsheet will be to create the 8 plots that you see here. On the upper row are the wave function plots themselves, and on the bottom row are the square of the wave functions. And so the square of the wave functions are the probability density, and where those peaks are highest are the places that the quantum harmonic oscillator's particle is most likely to be found. So I found it when I was building this spreadsheet that it was a bit easier to keep things organized if I put the plots on a separate sheet than the actual calculations. And so what we're going to put into the next sheet as we build it are some constants, some inputs. So don't mess with the constants. The inputs you can customize to be what you want for your configuration. And the intermediate values are single values calculated off those inputs that are then used by these sequences of values to the right. So let's start with building our own spreadsheet step by step. So let's start building the spreadsheet out step by step on 2 new tabs. So I'm just going to call this one Build Calc. And now zoom in just a bit so that it's easier to see on the screen. And so the first section will be our constants. Make it go bold. So we have h, Planck's constant, would be 6.626, e to the negative 34. We have h bar, which is equal to that divided by 2 pi. And we have c, which is the speed of light, in meters per second. We have inputs. So I'm going to, since we're going to be using reduced mass, we're going to have inputs for 2 masses, mass 1 and mass 2. So I'm going to assume that that's going to be a hydrogen chloride molecule in the gas phase. So not HCl acid, which is dissociated, but HCl, the molecule, which is connected with a bond. And that 1 mass will be that of chlorine 35, the most common isotope of chlorine, and the other mass will be that of a proton, so just the most common isotope of hydrogen. So mass 1, 1.67 e negative 27 kilograms. Mass 2 is 5.81 e negative 26 kilograms. K is going to be the spring constant, and I also found this on the hyperphysics site, which is 481 Newton meters. Let me go ahead and put some units in here, kg,
Newton meters, and joule seconds, meters per second.
X min, and I'm going to say that this is negative 5e negative 11 meters, and X max, 5e negative 11 meters. And these min and max values are the range of the x-axes on all the plots. So they're all the points that we're going to be calculating the function at. So that brings us to our intermediate values. Intermediate values, which are MR for reduced mass. And that's going to be equal to the product of these two masses. So this times this divided by their sum, this plus this. So then omega, the angular velocity, which is going to be our square root of k over mr. So it's going to be equal to square root of k divided by mr. And then what we're going to have finally is alpha, which is going to be h bar squared divided by the reduced mass divided by k, and 0.25 to the 1/4 power. And I just divided twice there instead of dividing and then putting parentheses and multiplying. I think it's a bit easier that way, easier to read the formula. And so we have, for omega, we're going to have 1/2, and alpha is just part of the wave function. So let's keep going with the sequences of numbers that will define our functions. So the first thing we need to do is create a line of numbers on the x-axis. So I'm just going to make these linearly spaced numbers. So the first thing I'm going to do is make an I sequence. And I'll put that in bold. And I'm just going to use the sequence function. And what that will do is spill out a sequence of numbers over adjacent cells that I tell it to do. So I want to make this from 0 to 1,000 inclusive. So I'm going to say 1,001 rows, 1 column, start at 0, step size 1. And we have our numbers. So then we need to define our x's. So what's on our x-axis? So that's going to be x, and I'm going to make that bold too. This is like a y equals mx plus b situation. So first we're going to define the slope, then we're going to multiply that by one of the i's, and then we're going to add the intercept, which is the minimum part of the axis. So what do I mean by that? So we're going to have x max, and then we're going to use function f4 to make that an absolute reference, minus x min, function f4, divided by 1,000 times I over here, plus the minimum of the axis. So we can see that we get starting at -5e -11, and it goes down to, well, it keeps on going down to the other extreme of the axis from there. So then the next column up is the gamma column. I'm just going to call this gamma. And that's going to be x over alpha. So that's pretty easy. That's going to be x divided by alpha. Okay, from here we need to build out the factors of our wave function piece by piece. So I'm going to start first with the Hermite polynomial. So I'm going to call these columns h0, h1, h2, and h6 for the Hermite polynomials we'll be using. V equals 0, v equals 1, v equals 2, and v equals 6. And for h0, that's really easy. That's just going to be 1, and just drag 1 down everything, because that's just the result of the function. And then h1 is going to be 2 gamma, so it's 2 times gamma. Nothing hard about that. h2 is going to be ever so slightly more complicated. 4 times gamma squared minus 2. There we go. Okay, finally, Hermite polynomial number 6. This is the fun one to enter. And by fun, I mean, we'll struggle together, but we'll get through it. So 64 times gamma to the 6th minus 480 times gamma to the 4th plus 720 times gamma squared minus 120. So now let's define a bunch of b's. And so what do I mean by that? I just want columns filled with just each one has a bunch of the same quantum number. So V0, for example. Guess what? Zeros. V1, same deal. V2, same thing. And V6, same thing. Okay, so N0, N1, N2, N6. These will be our normalization factors. And so I'm going to do is define one normalization factor formula here, use relative references out here to this V0, and an absolute reference down here to this alpha, and then just drag it to the right, and then double click to send it down, and fill in all of these normalization factors at once. So that'd be the square root of 1 divided by alpha times the square root of pi times 2 to the power of v times factorial v. Okay, so that closes that parenthesis. That closes that parenthesis. Just a second. That should do it. And of course it wanted to format it as general, but I'll fix that in just a moment. Drag that across, drop it down, select all these columns, format them as scientific. There we go. Okay, so now's the time to actually make the values of the wave function itself. Very, very exciting. So I'll call these columns psi0, psi1, psi2, and psi6. And then this is going to be equal to n0, so the normalization factor, times the Hermite polynomial, times exp of negative gamma squared and because we have the right mix of relative and absolute referencing, there we go. There's our values of the wave function. Okay, so now it's time to actually make the squares of the wave functions, and this is going to be surprisingly easy. Well, I'll just say this, it will be nice and easy. So psi0 squared, psi1 squared, etc. This is going to be equal to that squared. And I can get away with squaring it like that since we're working with real valued functions and not any sort of complex functions where we need the complex conjugate. So just keep that in mind. And there are squared wave functions. Now let's plot. Rename into build plots. And just start inserting plots. So I'm going to insert a scatter plot type with straight lines. Select data. Grab my x values first. Then grab the psi values next. And there's psi0. Okay, so let's move on and make the plots of the square of the wave function. I'll just proceed as before. And finally remove the grid lines. And there are our plots. Let me change the colors on these plots to make it a bit easier to discuss them. Okay, so there we go. So to me, what sticks out with this analysis are, as I see, the most important plots graphically are the bottom row of orange plots. And so we can see at v equals 0 that the particle is going to sit at the equilibrium position, most likely. Then at 2, it's going to have 2 places around the equilibrium it's going to be equally likely to be found. But as you move up to v equals 2 and then v equals 6, you start to move out to where you're most likely to find it near the edges of the system, because those bumps are higher, and that even becomes more pronounced as the Hermite polynomials go up in the wave function. So there you go with the visual analysis. So I hope you found this an entertaining use of Excel for quantum modeling. I had a lot of fun doing it, and I hope you had a lot of fun watching it. And if you like it, please like it, subscribe, and leave a comment. I'd appreciate it. Thanks for watching. Bye.